So last time, we got to the concept of form momentum. So I sort of upgraded the regular mechanics to relativistic mechanics in space-time. And so now we have space-time position, space-time velocity, and space-time momentum. It's an object that has four components: the time component and the spatial component. And as the particle goes on a trajectory in space-time called world line, we can assign a quantity called form momentum. And that if you have multiple particles and they somehow interact, let's say there's a collision, there's something going on, and you have the reactants and the products, as long as the total system is isolated, that quantity, that form momentum, the total form momentum will be conserved. So the form momentum I used this kind of notation. It has four components: the temporal component, and then gamma m ux, gamma m uy, and gamma m uz, the four components. And to remind you that u sub x, for example, it's the ordinary velocity of a particle in any given frame. Dx dt, uy equals dy dt, and so on, okay? And I want to clean this up a little bit. So the spatial part of the form momentum, this is the spatial part, is called relativistic momentum. And I will just denote it by P as a vector. It's a vector P, but it's not an ordinary P. It's not mass times velocity. It's gamma times mass times velocity. So relativistic momentum is gamma times mass times the velocity, or mass times velocity divided by 1 minus u squared over c squared taken square root. So the upstairs is regular or non-relativistic momentum. And in relativity, when we say momentum, what we really mean is we mean this thing, okay? So we see that relativistic momentum thus defined as just gamma times the non-relativistic momentum. And although this is just the definition, we simply gave the name to this quantity and called it momentum. This name is justified for two reasons. So first, it reduces to the conventional momentum at low velocities. So when u, without vector, it means just the magnitude, is much, much less than the speed of light, you can show that mu divided by 1 minus u squared over c squared. You can do a Taylor expansion, and it becomes mu times 1 plus 1/2 u squared over c squared plus higher order corrections. They're smaller and smaller if u is much less than c. And we see that, so this is small, and this just approaches regular momentum. So that's the first justification for why we call this object relativistic momentum. It nicely reduces to ordinary momentum. You can see it directly from this expression that when u over c is much less than 1, the denominator containing square root basically goes to 1, and you basically get regular momentum. And second, we will see that in an isolated system, this quantity, the relativistic momentum, will be one of the quantities that remains conserved, the other being the relativistic energy. This is what we expect of momentum. And indeed, the reason why the word momentum is even used in physics, it's because it's simply a quantity. It's one of the quantities that remains conserved for isolated systems. Okay, so what's important is not what it's called, but its utility. And utilities have the quantities that have an important utility are simply given a name. Okay, and then there was the temporal component. Let me use use orange. Okay, so this is the temporal part. Okay, the temporal part temporal means the part that's inherited by the time slot in the 4 vector. Because remember, this whole thing started with time, or CT. And we took derivatives multiplied by m and so on. So that's the temporal part, or the time component. So we can write it as, so this is gamma mc. We can write it as gamma mc squared over c. And the quantity gamma mc squared is defined to be the particle's total energy. So total energy equals gamma mc squared, which is mc squared divided by, again, 1 minus u squared over c squared, taken square root. Okay. Again, this is just the definition. You might say, well, you can call it whatever you want. Why did you call it energy? And we will justify it, but we can begin to justify it again by examining what this quantity does at low velocities. So note, when u is much, much less than c, that is, u over c is much, much less than 1. This energy becomes, again, we can do Taylor expansion, because mc squared times 1 plus 1/2 u squared over c squared plus dot, dot, dot. And this is mc squared plus 1/2 mu squared, okay? And we recognize the second term as the kinetic energy. You could say, oh, look, this is just conventional, this is conventional kinetic energy that's familiar to everyone. Okay. However, you can see that there is a term that remains non-zero even when velocity is 0. This little guy right here pops up, which we normally would say, well, that's just a constant. You can always add a constant to energy. But we will see that since the 4 momentum has to be conserved, what has to be conserved is the grand total of this mc squared plus the kinetic energy part plus the 4 momentum part. And nowhere does it say that mass has to be conserved. So this term is no longer constant. Mass will be no longer constant. There is just nothing that says that mass has to be constant. It's simply assumed in pre-relativity. So if I stuck on a term like this, mc squared, that's like adding 25 to energy. You can add any number to energy. However, it's not actually a constant. because again, what has to be conserved is the four momentum, which has this energy part and the relativistic momentum part. That's what has to be conserved. The mass, there's no rule that says that the mass has to be conserved. Okay, and so in any case, we have two parts to the energy. The part that depends on velocity, which is all these terms, and this little bit that's left, okay? And the term that remains, this little bit that's left, it stays non-zero even at zero velocity. So if the whole term is energy, and this is the bit that's left when velocity is zero, then the logical term for this is rest energy. Okay, so this is it's often denoted like this. This term seems to associate mass with energy. And for this reason, it's also called mass energy. Okay? So again, you may claim we just called it energy. But again, what matters is not what it's called, but its implications. And we will see that one of the implications is that it's not the mass that has to be conserved, but rather the total energy. And in a sense, that will imply that mass and energy are sort of one and the same thing. You can have energy that's in the form of mass, and then it becomes in the form of, say, kinetic energy, while the mass, the actual mass, becomes smaller. Okay. So we will come back to digesting this famous term, rest energy equals mc squared. We'll come back later, maybe in the third section of today's lecture, and really digest it. Okay. In any case, for now, the four momentum is made up of two parts, and it can be written compactly as E over C and the relativistic momentum. Not the ordinary momentum, but the relativistic momentum. The spatial part of the four momentum. And note that the split of the four momentum into energy and relativistic momentum depends on a particular frame. This object is a four vector, okay? And so since the four momentum is a four vector, when we switch from one reference frame to another, what was the energy part, the time part, in one frame becomes a combination of the momentum part and the energy part in another frame, okay? And so what was energy part in one frame will becomes a combination of a different, of momentum and a different value of energy in another frame. That's what I'm trying to say. However, as with any four vector, there is an invariant quantity. And I gave you an example, some generic four vector A that has parts A naught, A1, A2, A3. What would be the invariant? Minus A naught squared plus A1 squared plus A2 squared plus A3 squared. Well, here you go. Here's a vector. Here's a four vector. So there is an invariant. Just a second. I want to switch colors, so I'm going to pause. So there is an invariant. Which is minus E squared over C squared plus T squared. Or if I write in terms of components, minus A squared over C squared plus EX squared plus BY squared plus BZ squared. Remember, this is relativistic P, so it has the gamma in it, gamma times the regular P and V. Okay. If the particle has a mass, we may evaluate this in its own rest frame. Things that don't have a mass, they don't have a rest frame. But if the particle has a mass, we can switch to the rest frame of that particle, we can always catch up to it. And in that frame, it will seem stationary. So we may as well evaluate this in the rest frame, right? In the rest frame. Okay, so in the rest frame, the momentum of the particle is 0, and the energy of the particle is just the rest energy because its kinetic energy is also 0. In other words, so this quantity is an invariant, so we may as well evaluate it in the particle's own frame. And so we come to the conclusion that rearranging some terms, so this is the magnitude of the vector, I'm not writing it out explicitly in terms of components, equals m squared c to the 4th. So this is a very useful relationship because it links energy to momentum without mentioning velocity. Okay, the total energy of the particle to momentum without mentioning velocity. So this is a useful expression that we might need later when we do quantum mechanics. And yeah, that's what I want to say. It will be instructive and useful to digest all these things, to look at a particular example. So let's look at an example. So this is a collision. Basically, same type of example that we used to digest invariance of momentum and energy, but now we will do this in the relativistic realm. So you have a particle of mass m1 moving to the left, sorry, to the right, and particle of mass m2 moving to the left. So this one has u1, velocity u1 initial, and this is u1 final. Okay. They collide. For simplicity, let's say the particles retain their identities. So after the collision, so this is before, and this is after. So let's say, for the sake of simplicity, let's say they retain their identities, but the same analysis holds even if the reactants of products are not the same, and therefore even if the masses are not the same. So this one will have u1 final, this has u2, this should say 2, u2 final. See, in this case I caught my slip of a tongue or a little typo, things like that happen all the time, but I'm trying to catch them. Okay, so for simplicity, let's say they retain their identities, and after the collision we have m1 moving with u1 final, and m2 moving with u2 final. Now recall that we want the law of conservation of momentum to be invariant. That means that if momentum, and I'm talking about just the spatial part, the momentum or the relativistic momentum, not the four momentum. So that means that if momentum is conserved, then it has to be deemed conserved in any other frame. Before, we switched from frame to frame through a Galilean transformation, but now we know that it's not a correct way to switch from frame to frame. Thus, now we know that principle of relativity really means that a law is Lorentz invariant, not Galilean invariant. So to begin with, let's check if the classical momentum, just regular vanilla mu or mv, I'm using u here for velocity, so mu, let's check if that quantity is Lorentz invariant. Okay, so let's say in one frame, check if mu is Lorentz invariant. Okay, so let's say in one frame, it is true that you have momentum conservation using this expression for momentum. Let's say that it is true. And the question is, just like in that homework, would it still be true that the form of the relationship, the form of the law remains the same? I still get questions from students that indicate that they don't understand what it means to say the form of the relationship remains the same. I.e., question, would it be true that M1 U1 initial plus M2 U2 initial equals M1 U1 final plus M2 U2 final? This, if this is true, you can see this has the same form, it has the same structure. It doesn't have any extra terms. Well, let's check. Let's do the checking. Well, we know how velocities transform. So we are doing relativistic calculation, but we're guessing the form of momentum. And if it's conserved, we'll say, okay, that's a good definition of momentum. If it's not conserved, we'll throw it away. Again, the reason the word momentum exists in the dictionary is because it's something that's conserved for an isolated system. So let's see. We know how velocities transform. So starting with the supposed momentum conservation in the unprimed frame, we can transform to the primed frame, just like you did in the homework. You did it using Galilean velocity addition rule. Okay, now we do it correctly. So we apply relativistic velocity transformation rule, right? Just like in the homework, I'm following in the same footsteps. So I'm gonna write down what that looks like, and you can convince yourself that that's correct. So we have M1 times, this is gonna be kind of a long expression, and what do I put here? You should know, it's just both of these, product of both of these terms. Sorry, this is supposed to be initial. See, I'm getting good at catching typos. So I'm taking the expression that I know is true, and I'm just applying the transformation. So this must be true. So this is not a question mark. This, what I'm writing down, is true if the star expression is true. So let's see. Let's see. So the final, now I'm going to apply the velocity change rule. Okay. Okay. So notice what happens. So I have this pesky new terms right here that if I didn't have them, the sum m1 plus m2v on the left would cancel with m1 plus m2v on the right. And we would indeed have this form, this kind of thing. But I do have those denominators. Okay. And because of those denominators, we see that if the sum of the products of m times u is conserved in one frame, in other words, that sum is the same initial and before and after, that in general, the sum of the products of m times u tildes is not conserved in another frame. In other words, that sum initially is not the same as the sum finally because of these denominators. Without the denominators, the statement would be true. So we need to, if I had to guess, I need to fix my definition of momentum, right? So mu does not work. You can, of course, call it momentum. You can call it anything you want. You can call it furry cat. But it's not a useful quantity. It's not conserved. Okay, so we can scratch our head and we can try to guess. But I already told you what the relativistic, I already gave you a suggestion. Let's try the suggestion, okay? And you can probably already see what's gonna happen. The gamma, it will allow us to cancel things, but it's a little bit more involved than that, right? So let's say P initial net, the total momentum, equals, actually, let me just, so why am I writing the subscripts? What do I mean by gamma? Gamma is 1/1 minus u squared over c squared. So there is a u mentioned inside gamma. And what we want is we want this u to be the same as this u. So if we apply this definition, it means that the u that goes inside this gamma is this u, but the u that goes inside this gamma is this u. Okay, that's the meaning, that's the reason for these subscripts. The values of these two gammas are not the same. Okay, but that has to be true. That's what we mean by momentum here. Okay, so let's say it is true that the relativistic momentum is conserved in one frame. Okay, a little bit of a mouthful, I know. But basically we have 4 gammas here. Other than that, the expression is the same as the non-relativistic one. Okay, you can wrestle with algebra all day long, but the following identities help. And I will tell you where they come from. So gamma u prime equals 1 minus ub over c squared gamma u gamma v. These are very interesting identities. Equals 1 plus u prime v c squared. You can guess gamma u prime gamma v. Okay, and where did this come from? They seem like they arrive out of the left field. And one can show that these come from the invariance of from the invariance of the for momentum, from the invariant that comes along with for momentum. Remember that the for momentum, it's a 4 vector, so it has an invariant, and that invariant gives rise to these things. But anyway, for now, I'm just giving them to you. And when we use these, when we use especially the second, I'm going to use the second of these, and again, do the velocity transformation. We get, you can do the algebra for yourself. I'm just going to give you the result. We get the following thing. I have to be very careful about what I write. M1 gamma U1 tilde initial times U1 tilde initial plus M2 gamma U2 tilde initial. Again, there's a U that's mentioned inside gamma. So I have to specify what that U is. U2 tilde initial. Plus, there's something else here. M1 gamma U1 tilde initial plus M2 gamma U2 tilde initial times V. And that will remind you of something like that, except that it didn't have the gammas when we did the non-relativistic calculation. Okay, so I have M1 gamma U tilde 1 final U tilde 1 final plus M2 gamma U tilde 2 final U tilde 2 final. These are subscripts, these are multiplications. Plus M1 gamma U1 tilde final plus M2 gamma U1 U2 final times V. Okay. So let's try to understand what's going on. These are the relativistic momenta in the new frame. Is the form of the relationship the same? No, it's not. We have these annoying extra terms. So is the momentum, is the even relativistic momentum conserved in the other frame if it's conserved in one frame? Not unless these things are also conserved. So the momentum is indeed conserved in the new frame only if these strange quantities are also conserved. So this equals this only if I don't know what color should I use. Only if this equals this. Okay? And what is that quantity? It's just energy divided by C, as we defined it. Actually, let me do this. But remember, E equals gamma mc squared. So then this right here is the total initial energy of particle 1. This is the energy of particle 2, the initial energy of particle 2, final energy of particle 1, final energy of particle 2. Okay? So we learn that in relativity, energy and momentum have to be conserved together. In regular physics, if you have an elastic collision, the kinetic energy of that system will be conserved if it's an isolated system. But if it's an isolated system, then momentum is also conserved. However, the conservation of momentum does not involve any arguments about energy, only that the system is isolated. In relativity, if one is conserved only if the other is conserved, and the other is conserved only if one is conserved. So I'm going to stop the first video, the first part on this. That's a lot of information to digest. And then we'll continue this discussion.